In this video, we are going to look at a couple of examples of Z transforms. So this is a small tool which will allow us to visualize. So you need to specify B and A, which are the coefficients of the numerator and the denominator of the Z transform, and then we can observe the pole zero plot as well as the magnitude and phase response for the filter. Notice that we will always be choosing that magnitude and phase response. We will be choosing that filter which always contains the mod Z equal to 1 within the ROC whenever a confusion rises. So let's take 1, 1, 1, 1, 1. So let's say it's like 6 ones. Okay, if we take 6 ones, okay, that's delta n plus delta n minus 1 up to delta n minus 5. We see that there are exactly 6 zeros. 6 zeros, and we don't have any poles. Of course, you can always argue that there's a pole, it's 0. We are ignoring the poles at 0 and infinity, but there are 5 zeros. Okay, and these zeros are exactly at the roots of the polynomial 1 plus z inverse plus z power minus 2 and so on. You can also see that the magnitude response looks like this and the phase response looks like this. Okay, so let's make some changes. Let's look at the filter. Let's look at a sequence which has something like 1, just 1, 1. You know that this has 1 plus z inverse. So 1 plus z inverse is the sequence. It has a 0 at minus 1, because if you substitute z as minus 1 you get 0. So clearly there is a 0 at minus 1, and they also claim that there is a 0 at 0. We'll ignore those for now. So you get this 1 plus 1 plus z inverse has this kind of magnitude response, and this is the impulse response. Okay, this is fine. Let us look at something a little more interesting. What about 0.9 power n un? So you know that 0.9 power n un has a z transform of 1 upon 1 minus 0.9 z inverse. So in this case, we see that this is 0.9 power n un. There is a pole at 0.9, and that gives you this kind of impulse response. So you get a pole at 0.9. So let's try changing that 0.9 to 0.5. You will see that the pole moves closer to the origin. It moves to 0.5. You see that the sequence decays much more quickly, and you see that the magnitude response also flattens somewhat. So as you will see in the next part of our discussions, you will find that a power n un for positive values of a acts like a low pass filter, and the higher the value of a, the more the averaging that it performs. So more is its low pass filter characteristic, which is why if you make this something like 0.9, you will see that the lower frequencies get higher gains. If I make it 0.99, you will see that it's actually falling really slowly, and there's a huge boost at DC, while other values seem to have been suppressed. Okay, next let's actually look at something like the convolution of a power n un with delta n plus delta n minus 1. So this is 1 plus z inverse by 1 minus 0.9 z inverse, mod z greater than 0.9. So now interestingly we have a 0 at 1, because the 1 plus z inverse has a 0, and then we have a pole at 0.9, and the 0 at 1 causes, we have 0 at minus 1 rather. 0 at minus 1 causes the response to go to 0 at pi, and this is the impulse response that we end up getting. Notice that it's actually a power n un plus a power n minus 1 u of n minus 1. That is what causes this. So suppose that you want to just have a power n minus 1 u of n minus 1, you add a 0, you'll find that it starts with a delay, and now you have this kind of a functionality where you have the same magnitude response. In fact, the magnitude response will not change at all. If I add as many zeros as I add, you'll just see the magnitude response remains the same. You just shift it, it remains the same, primarily because the magnitude response doesn't depend on delays, it remains the same. Okay. Next, Let's do a couple more examples. Let's make the denominator 1. Let's do something like 1, 2, 3, 4, 5, 6, 7, 8. Okay. Notice that this is still a finite impulse response sequence. Okay. This has this has actually all its zeros outside the unit circle. That's not a problem. Having zeros outside the unit circle is not a problem. Finite impulse response sequences are always stable and has this kind of a response. Okay, let's do something a little more interesting. Let's do 1, 0.9, 0.8, 0.7, okay, 0.6, 0.5, 0.4, 0.3, 0.2, 0.1. Again, this is a sequence which has several zeros. It falls roughly linearly. It acts like a low pass filter because it does do some kind of averaging. Okay, so you can sort of see it. But what if you have a sequence like this, 1, minus 1, and say another 1 and minus 1? This sequence is going to have a 0 at 0 and a 0 at pi by 2 because it actually nulls those frequencies out. But more importantly, it has zeros at 1, j and minus j. So those are the non-trivial zeros. Notice there are no poles because it's a finite impulse response sequence. So now you can combine this with things like 1, if you convolve this with minus 0.9 power n un, you can get some different kinds of sequences. And you can sort of play around with it to see what you get. I have basically introduced a pole. Suppose I introduce another pole. So I introduce another pole in this manner. Then you get this kind of effect. So all these kinds of things can be studied. Okay. So this tool is, I'll give you the source code for this tool. I'll put it in the description below. You can run it yourself if you're interested. Thank you.